Hi, this is Chris M. And in this video, we are going to continue with vectors. We've looked at vectors in component form now, and we're going to be talking about adding and subtracting these vectors in component form together. And then we're going to be talking about a new form that we can put these in, which is equivalent to component form. When we have two vectors in component form, it's really going to be easy to put these together. So when you have vectors in this component form, we can put them at the origin, and you might recall the parallelogram method. We're going to be using this method to add them graphically, but really we're just looking at trying to find the algebraic result, which is super easy. So let's just take a look at these vectors really quickly here, and then I have some examples for us to do. Here we have the vector u, which is at 6, 2, and the vector v, which is at -3, 5. If you check those vectors out, below, you have the two tails of those at the origin, and they're terminating in quadrants 1 and 2 respectively. Now, when we want to find the sum of those, we complete the opposite sides, and we can use that parallelogram method to add them together. So our result is going to be that blue vector. But look at how easy it is to add these vectors together in component form. So if I want to try to find u plus v in component form, essentially what I do is I add the x components together and I add the y components together. It's that easy. So let's check this out. So u plus v would be -3 plus 6, comma 5, the y component, plus the y component of the second vector, plus 2, we would have 3, comma 7. And bingo, that's exactly where those terminate over there. Super simple to add these together. Another thing we can do is scale these. Let's say that I wanted to take 2 times vector u. All I would do is take the scalar 2 and multiply it by each component. So 2 times the vector u would be 2 times -3, comma 2 times 5. And this will result in 2 times 5. It looks like I prematurely did that multiplication. -6, comma 10, right? So if I scaled this vector u and made it twice as big, there we go. I should be at the point 10, -6. Looks like I did v. So let's look at v here. This would be v. So let me double v. There we go. So this is another v. So now let's see if this works. -6, great. And +10, yes. So that is how we scale vectors together. So you might see, well, actually, Chris, you did v plus u instead of u plus v. The thing is that these are commutative. So when we add these together, I can add them in any order. So u plus v is the same as v plus u. It'll totally work out that way. Woo, okay. Let's go ahead and look at this second form here. So the second form is called component vector form. Component vector form is something that you'll see if you take physics or calculus. So they introduce it here. They actually write these vectors as a linear combination of what we call unit vectors. So unit vectors have a unit length of 1, and they have directions on the axes. They talk about these two special unit vectors. We have the unit vector I. Sometimes I call it I hat, or I put a arrow over the I. It terminates at 1, 0. So length 1, on the x direction, it describes the x direction. And j, or j hat, or j with the arrow over it, is the vector 0, 1, and that describes the y direction totally. Now, with three-dimensional vectors, you'll see a k hat too, or a k vector, and that will be coming right out at you. That'll be the coordinate 0, 0, 1 if you're getting into 3 dimensions. We're not going to do that in this class. Okay, so we can add these together so easily as well. So for instance, I can show you how to do this, but quickly, if I had the vector u in component form, like 6, -2, then I could write it as a combination of 6 times the vector I plus a -2 times the vector j, or that would just be 6i minus 2j. So these would be the total same thing in component form and component vector form. So each one of those would be the exact same thing. Okay, let's take a look at some examples here. So I'm going to share my screen, my .cam, and I'm going to be looking at adding these vectors together, subtracting, and then taking multiples of these. I just have 2 vectors here. So u plus v, if I have 5, 2 plus 4, 1, I just add those components. So I have a -5 plus 4, that's -1. And I have a 2 plus 1, that's 3. So if I added those 2 together, my result should be at -1, comma, +3. And you can sort of see that. So -1 up 1, 2, 3 should be like this. If I made the parallelogram, okay, there would be my opposite side of u. There would be my opposite side of v. Yeah. So that would be my u plus v. What about subtracting these? Well, algebraically, it's pretty easy. I just subtract the components. So I'll take a -5 minus 4, comma 2 minus 1. So I distribute through, and this would give me a -9, comma 1. -9, comma 1. So if I have 5, 6, 7, 8, 9, let's just scoot that in on the screen, and a 1, if I subtracted those, it should terminate there. Well, how do I subtract vectors? I would take the u, which it looks like I've actually flipped these around again. So v minus u, I would take this u and make it negative. So this is my negative u. And so if I took v plus negative u and use my parallelogram, yeah, I'm going to be over here at v minus u. At that point, -9, 1. So this is something, my mistake here is actually going to tell us something else. When we're subtracting vectors, it's not commutative. So I need to be super careful, and I need to say, all right, this was actually v minus u. V minus u. Okay, let's try this one again. So I have, this one's going to be 2 times v minus 3 times u. So algebraically, we can go ahead and work this out. I multiply through, I get -10, 2 times 2 is 4, minus 3 times 4 is -12, minus 3. So I distributed the minus through, and then I add those together. So -10 plus -12 is -22, and 4 minus 3 is 1. All right, let's see how we do this with the component form. So here, I have vector u and vector v. If I add these together, I just take the i's and I add them together. So 2i plus 5i is 7i, and 5j plus 2j is 7j. If I added these two together, I'd be going over 7, 6, 7, and up 7. So adding these together should put me around here at 7i plus 7j. And notice if I made my opposite sides of the parallelogram, that should work. Okay, let's look at u minus v. Here again, I just need to distribute. So I have 2 minus 5 I hat, and I have plus 5 minus 2 j hat. That's going to be negative 3i plus 3j. So these are really easy to combine with scalar multiples and adding and subtracting them together. Linear combinations of these unit vectors. Let's look at 2u minus 3v. Here, if I distribute through, that's going to be 4i plus 10j minus 15i minus 6j. And now again, I'm going to add the i's together. So 4 minus 15 is negative 11i, and 10 minus 6 is plus 4j. So there's my vector in that component vector form with the unit vectors. One more example is if I have these vectors and with just the magnitude and the angle given, I can write them in this form by using the vector is equal to, and we've talked about resolving these into their components. So the horizontal component, which would be the magnitude times cosine of the angle theta, I, plus the magnitude times sine of the angle, j. This is going to give me my horizontal and vertical component. So I plotted my vector here. It's about 5.8. And my angle here is 71 degrees. If I wanted to find the horizontal component, that's just the magnitude times cosine of 71, almost 1.9. So this is close to 1.9. The vertical component, the magnitude times sine of that angle, I got almost 5.5. And that does make sense when we look at the picture. So my vector in this component vector form is going to be 1.9 I. So 1.9 of these I vectors here, plus 5.5 of these j vectors here. And that's going to be my answer. So I hope that this has helped you with the new vector form. Looking at these graphically and the ease of adding, subtracting, and multiplying them by scalars. So basically taking linear combinations. Thank you.